All right, we are looking at section 2.3 and just reading the textbook again. This time we are talking about the limit laws. Okay, so learning objectives. So we should be able to recognize basic limit laws, use the limit laws to evaluate the limit of a function, evaluate the limit of a function by factoring. So this is a common method we'll use. Use the limit laws to evaluate the limit of a polynomial or a rational function. Those turn out to be not that difficult. Evaluate the limit of a function by factoring or by using conjugates. Okay, so again, with factoring and maybe using conjugates. Those are important methods to know. And then finally, evaluate the limit of a function by using the good old squeeze theorem. Okay, so we've already talked about the basic idea of a limit. And so we're going to, we're going to come up with ways to find limits without actually necessarily graphing the function. Okay, so in the previous section, we illustrated limits by looking at graphs or by constructing a table of values. In this section, we establish laws for calculating limits and learn how to apply these laws. In the student project at the end of this section, you have the opportunity to apply these limit laws to derive the formula for the area of a circle by adapting a method devised by a Greek mathematician, Archimedes. We begin by restating two useful limit results from the previous section. These two results, together with the limit laws, serve as a foundation for calculating many limits. Okay, so evaluating limits with the limit laws. The first two limit laws were stated in two important limits, and we repeat them here. These basic results, together with the other limit laws, allow us to evaluate limits of many algebraic functions. Okay, and we look at these during lecture, actually, hopefully you attended that. Theorem 2.4, the basic limit results. For any number a and any constant c, the limit as x approaches a of x is a. Okay, and we went over that. That's pretty clear. Then the limit as x approaches a of a constant function c is equal to c. Okay, again, that's not too unexpected. So example 2.13, evaluating a basic limit. Evaluate each of the following using basic limit results. Okay, well, what is the limit of x as x approaches 2? Well, that would be 2, because if x is approaching 2, then this x is approaching 2, right? What about the number 5, right? The number 5 is constant. It's always 5. So as x approaches 2, what is happening to the number 5? Well, it is just staying the number 5. Okay, so yeah. All right, and there's the answers, the solutions. Okay, using those two limit laws, we should memorize these. We now take a look at the limit laws. The individual properties of limits. The proofs that these laws hold are omitted here. So, most people probably don't want to see a proof for all of these limit laws. Yeah, so, okay, so that's okay. Now, okay, so what are we given? Theorem 2.5, limit laws. Let f of x and g of x be defined for all x values not necessarily equal to a over some open interval containing a. So, because when we're talking about limits, we're talking about values getting closer and closer to a, but we don't really care exactly what happens exactly at a, right? So that's why we say x is not necessarily equal to a, but we're talking about x is over some open interval near a, containing a. And assume that L and M are real numbers such that the limit of f of x as x approaches a is L, and the limit as x approaches a of g of x is M. And then we're going to define c to be a constant. then each of the following statements hold. Okay, so the sum law for limits, and I maybe I'll write a couple of these down. Basically, how do you find the limit? Because from algebra that you can take a function and add it to another function. And these two functions added together is a new function. So if this is now a new function, the sum function, what is the limit as x approaches a of this sum function? And it would, it makes sense that it should be just, well, the limit as x approaches a of the first function plus the limit as x approaches a of the second function. And if these two limits exist, we said that the first one was L, the second one was M. So we would just add those two limits. So nice, good thing we have this property. And it works exactly as we would expect it to. The difference law for limits, this is almost the exact same thing, except it has a minus sign in the middle. Okay, what about the constant multiple law for limits? The constant multiple law for limits says, well, what if we have a function f of x and we know that the limit of this function as x approaches a is L, but what if we multiply it by c? Well, this c can actually be factored out of the limit. And so we would have c times the limit, and the limit has a limit value of L, so the answer is c times L. So again, this works exactly as you would expect. Okay, hopefully this is not like, whoa, that's strange, but it's just like, okay, yeah, I mean, that makes sense. The product law for limits. The limit of a product of two functions, f and g, is just the product of the two limits of f and the limit of g, right? So it breaks up into the limit for f, the limit for g, and those are L times M. Okay, very good. The quotient law for limits, again, a similar idea here. This is kind of what we would expect. The limit of a quotient f of x over g of x as x approaches a, we just take the limit individually, the limit of the numerator, the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. The top has a limit of L, the bottom has a limit of M, so it's L over M. But keep in mind that this does not hold, or this only holds if the limit of as x approaches a of g of x is not equal to 0. Of course, because, if this limit down here was 0, then this limit, L over M would be L over 0, which is undefined, right? So we can't have that limit is 0. Power law for limits, okay? Well, the limit as x approaches a of some function raised to the nth power of a function f of x raised to the nth power, what do? We can actually essentially kind of push this limit inside of that set of parentheses, and notice now we have the limit on the inside, and that entire limit is now raised to the n. And the reason this helps us is because we know what that limit is. That limit is equal to L, and then you just raise L to the nth power. And this is true for every positive integer n. And then the root law for limits in a similar way. We can, if we have the limit as x approaches a of the nth root of f of x, we can essentially push this into the nth root. And so now we have the nth root of the limit as x approaches a of f of x. Well, we know this has a value L, so this is just equal to the nth root of L. For all L, if n is odd, and for L greater than or equal to 0, if n is even and f of x is greater than 0. And of course, these little statements need to be made here for L greater than 0, because if L was less than 0 or negative, we couldn't take the square root of a negative, and that would make no sense. And then f of x must be greater than or equal to 0. Same thing here, because if f of x was less than 0, then you'd be talking about the square root of a negative number here, which may cause some problems there. So let's go ahead and practice applying these. And actually, before we show the solution at the bottom there, I like writing these out sometimes. This is definitely going to be a lot of writing for us right now. But it's kind of good to see the foundation of where how these limits are evaluated. So I'll write this one out, and then eventually we'll kind of stop writing them in this way. But the limit as x approaches -3 of 4x minus 2, I'm going to write this as the limit as x approaches -3 of 4x plus the limit as x approaches -3 of 2. So notice I split this up. I went 4x, I did the limit of that, and then 2, and then I did the limit of that. This is using the sum law for limits, right? The limit of a sum of two functions is equal to the sum of the limits of each of those individual functions. And then what else can I do? I can next use the constant multiple law for limits. And I can basically bring that 4x, I can bring that 4 out of that limit. And so this can be written as 4 times the limit as x approaches -3 of x plus, and this is still the limit as x approaches -3 of 2. And now notice that we've broken this limit down. What is this here? This was one of the basic limits that we went over in the last section, and we also reviewed in this section. And then this is the limit of a constant. These are the limit laws that were given up here in theorem 2.4. So these should be very easy to do. I'm going to put an equal sign here. This is going to be equal to 4 times the limit as x approaches -3 of x is -3, plus the limit of a constant 2 as x approaches -3 is 2. And so the limit here is -12 plus 2, which is -10. This is our answer, -10. And you might be saying, well, couldn't we just have plugged in -3 there? And the answer is yes. We're eventually going to get to that. But it's good to see the foundation here because, well, which limit law does it say that you can just plug in your number? None of these say that. But if you break down the limit to its most simple parts, then you can see that as long as you understood all of these limit laws and these previous ones right here, then we are completely justified in breaking it down this way and then evaluating our limit this way. Okay, so let's just read the solution. Let's apply the limit laws one step at a time to be sure we understand how they work. We need to keep in mind that the requirement at each application, that at each application of the limit law, the new limits must exist for the limit law to be applied. Okay, and then, so you see, apply the sum law, apply the constant multiple law, apply the basic limit result, and simplify. That's exactly what we did. Okay, using limit laws repeatedly. And so here's another one. And so before we look at the solution here, let's go ahead and just break it down ourselves. And we can actually, I'll do it one step at a time. So when we have the limit of a fraction, this is the quotient law for limits. If you see the quotient law up there, it says that you can take the limit of the top, 2x squared minus 3x plus 1, divided by the limit. Oops, and I should have put my little x approaches 2. The limit as x approaches 2, it is necessary to put that, of x cubed plus 4. So I did it, the quotient law here. I applied the limit to the top, applied the limit to the bottom. And then we're going to use that sum law, the sum law for limits and the difference law for limits. And basically, I'm going to apply the limit as x approaches 2 of 2x squared plus the limit as x approaches 2 of -3x plus the limit as x approaches 2 of 1 divided by the limit as x approaches 2 of x cubed plus the limit as x approaches 2 of 4. And you might be saying like, wow, this is taking a long time. And yeah, it is true that this does take a while. But the reason that we do this, when you say, oh, can't you just plug it in? Yes. And basically it would be after doing a few of these problems, you should recognize that you can just plug in your value. And in many cases that gives you the actual value of the limit. And we'll talk about in what specific cases you can just plug in your value and in which cases you can't. Okay, so, but in the meantime, we'll write it out. Okay, so what can we do? We can factor out this 2. And we can write this as the limit as x approaches 2 of x squared plus, I'm going to factor out, actually, I'm going to, instead of that plus, I'm going to put a -3 because I'm going to factor out that -3, the limit as x approaches 2 of x plus the limit as x approaches 2. And I really should have done this one here of 1, but that one's already simplified enough. Now, what am I going to do next? I'm going to apply to this limit as x approaches 2 of x cubed. I'm going to apply the power law for limits, because notice we have a function that's raised to the 3rd power, x cubed. And what it says is we can actually take the limit of the function and then raise that entire limit to that exponent. So let's go ahead and see how we're going to do that. This can be written as the limit as x approaches 2 of x, and then we apply the exponent to the entire limit plus the limit as x approaches 2 of 4. Okay, and I hope you don't mind, I'm going to cheat here just to make our step a little bit shorter. Instead of the function x squared here, I'm going to use that power rule for limits, and I'm going to apply that square to the limit here. Okay, and then what do we get? Let's go ahead and see. Then we're going to get 2 times the limit as x approaches 2 of x is 2, and then that's squared, minus 3 times the limit as x approaches 2 of x is 2 again, plus the limit as x approaches 2 of 1 is 1. The limit as x approaches 2 of x is 2, and that is being cubed. And then finally, the limit as x approaches 2 of 4. And notice that this is exactly this expression here evaluated at 2. You just plugged in 2. So yeah, I mean, after a while, it does become a pain to write these out, all these limits here. But we need to show that for a rational function, we can actually do this. It ends up coming out the same. So what do we got here? Arithmetic. 8 minus 6 plus 1 over 8 plus 4, which is 8 minus 6 is 2 plus 1 is 3 over 12 or 1/4. Okay, nice. So to find this limit, we need to apply the limit laws several times. Again, we need to keep in mind that as we rewrite the limit in terms of other limits, each new limit must exist for the limit law to be applied. Okay, so we applied the quotient law, which is what we did. Apply the sum law and constant multiple law. Yes, we did that. Apply the power law. Yes, they did that twice. And then apply the basic limit laws and simplify 1/4. Very good. So the limits of polynomial and rational functions. Now, here we go. By now, you have probably noticed that in each of the previous examples, it has been the case that the limit as x approaches a of f of x has just been exactly f of a. This is not always true, but does hold for all polynomials, for any choice of a, and for all rational functions at all values of a for which the rational function is defined. Of course, we can't have the denominator be 0. But notice that, yeah, we did one polynomial example in example 2.14, and then one rational function example. And it turns out, yeah, this theorem, theorem 2.6, tells us that the limit as x approaches a for a polynomial p of x, if we let p of x be a polynomial function and q of x also be a polynomial function, and then a be any real number, the limit as x approaches a of p of x is just p of a. You can just plug in a into your polynomial. The limit as x approaches a of your rational function p of x over q of x is p of a divided by q of a. You just evaluate both the top and the bottom at a. And of course, we need that q of a is non-zero. because then the function, you know, p of x over q of x is undefined. So, all right, very good. So to see that this theorem holds, consider the polynomial. And here we're going to give a general polynomial. P of x equals c sub n x to the n plus c sub n minus 1 raised to the x to the n minus 1 plus dot 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 c1x plus c naught. By applying the sum, constant multiple, and power laws, we end up with, and so we're taking the limit, right? The limit as x approaches a. So we apply the limit as x approaches a to the left-hand side, and we also need to apply the limit as x approaches a to the right-hand side. So when we do that, well, okay, here's a sum of a bunch of terms. Oops. So we apply the sum law, and that lets us, you know, add up, you know, limits. Now they're applying multiple laws here in this proof at once. So you're going to break this up by sums, by terms, but then at the same time, we're also going to factor out any constants like the cn out of the limit, and then the x to the n, that is going to be, you know, we're going to push the limit to take the limit of x, and then eventually raise everything to the nth power. Okay, so they're doing a lot of steps there at once. And then we can see that, well, this limit here is just a, this limit here is just a, this limit here is just a. So basically anywhere where there's an x, you're going to replace it by a. And that's the exact same thing as evaluating the function at a. Okay, so it's proven. It now follows from the quotient law that if p of x and q of x are polynomials for which q of a is non-zero, then, you know, the limit, this law applies for the limit as x approaches a of p of x over q of x. Okay, example 2.16 applies this result. So this is going to be way easier here. Oops. Evaluate the limit as x approaches 3 of 2x squared minus 3x plus 1 over 5x plus 4. And so one thing that we do need to note here that's given in the solution, it says, since 3 is in the domain of the rational function, then we can basically just use direct substitution. So this is equal to, now I guess you might know ahead of time by looking at this that x is, or that this rational function is undefined at, what would it be, negative 4/5, right? So 3 is definitely not making this function undefined, or this function is not undefined at 3. And, you know, you can always, I guess you can plug in and see. So 2 times 3 squared minus 3 times 3 plus 1 over 5 times 3 plus 4. This is equal to 2 times 9 minus 9 plus 1 over 15 plus 4. And this looks like it's going to be 9 plus 1 over 19. So 10 over 19, that is the value of our limit. Notice that that's way easier, but we had to kind of earn the ability to do this by noticing that those limit laws, you know, for polynomials and rational functions is basically the same as just plugging in your number. And so 10 over 19 is our answer. Okay, way easier. All right, what are some additional evaluation techniques? So as we have seen, we may evaluate easily the limits of polynomials. Yeah, okay, no problem. We had no problem there. The limits of some, but not all, rational functions by direct substitution. However, we saw in the introductory section on limits, it is certainly possible for the limit as x approaches a of f of x to exist when f of a is undefined. The following observation allows us to evaluate many limits of this type. If for all x not equal to a, f of x is equal to g of x over some open interval containing a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x. So let's take a look at this idea here. In this next example here, it says to understand this idea better, consider the limit. So let's write this out. The limit as x approaches 1 of x squared minus 1 over x minus 1. So here we can take the function f of x to be equal to x squared minus 1 over x minus 1. Now, we can see that this function is not defined when x is equal to 1, right? Because the function would have a denominator of 0 if x was equal to 1. So we can simplify, and let me write down here, and then we'll scoot this down here as well. We can simplify this function. Let's take a look here. The top factors, it's a difference of squares to x minus 1 times x plus 1. The bottom is just x minus 1. And so we can see that there's going to be some cancellation going on here, right? These x minus 1s can essentially cancel each other out. But once you cancel those, this is no longer the same function, because if you were to cancel these, notice that you would get just x plus 1 as your function. And I'm going to call this g of x for right now. The reason I'm calling it g of x and I'm not calling it f of x anymore is because if you look at this function, is this function g of x undefined anywhere? The answer is no. G of x is defined everywhere. Its domain is all real numbers because it is a polynomial. But f of x is undefined, at x equals positive 1. So f of x and g of x cannot be the same function because one is undefined somewhere and the other is undefined nowhere. It's always defined. So we would say that f of x is equal to g of x whenever x is not equal to 1. So if you wanted to, it says here, the function f of x and the function g of x are identical for all values of x not equal to 1. Okay, so the graphs of these two functions are shown. Let's go ahead and take a look at the graphs. Now, do you expect these two graphs to be identical to each other? Well, we shouldn't, because as we mentioned, one of these is undefined somewhere and the other is defined everywhere. Okay, so they should not be identical, but they should be pretty similar because we're saying that they're equal, except for at this one value of x. So let's take a look at the graphs, and we see the two graphs are almost identical, except one has a spot where it's not defined, and g of x is defined everywhere. Okay, the graphs of f of x and g of x are identical for all x not equal to 1. Their limits at 1 are equal. Yes, so because they only differ at this one value when x is equal to 1, the limit, as if we wanted to calculate the limit as x approaches 1, so as x approaches 1 from the left and from the right, we're getting closer and closer to a value of, it looks like 2 here. Now, if we, for some reason, like say, we can't do direct substitution with this one because this function is undefined at x equals 1. But if we use a very similar function that is identical to this, if we use a very similar function g of x that is identical to f of x for all values except for at x equals 1, well, that's perfectly fine because the limit actually doesn't take into account what's happening at x equals 1, only what's happening near x equals 1. And so we can actually, so the limit as x approaches 1 of f of x, which turns out to be this limit written underneath, can be simplified to this, and then you can divide, you can factor these or cancel those two factors there, and this ends up being the limit as x approaches 1 of g of x. Okay, so the limit, as you can see from that string of equalities, the limit as x approaches 1 of f of x is equal to the limit as x approaches 1 of g of x. These two are equal in limits, but they are not the same function when x is equal to 1. Okay, but remember the limit as x approaches 1 actually does not really pay attention to what's happening exactly at 1, just near 1. Okay. So we see that, okay, this string of equalities here, the limit, and when it says the limit has the form x, the limit as x approaches a of f of x over g of x, we are talking about this limit here, where you can see that the numerator, if you plug in 1 into the numerator, you get 0. So that's where this is coming from. The limit of the top is 0. And then if you plug in 1 into the denominator, you also get 0 for the denominator. In this case, we say that f of x over g of x has an indeterminate form of 0, 0. This is going to come back later in this class, the indeterminate form of 0 over 0. We're going to talk about the special case later. We're going to expand on it some more later. And then the following problem solving strategy provides a general outline for evaluating limits of this type. So how do we calculate a limit when f of x over g of x has an indeterminate form of 0 over 0? First, we need to make sure that our function has the appropriate form and cannot be evaluated immediately using the limit laws. We then need to find a function that is equal to h of x, which is equal to f of x over g of x, for all x not equal to a, right? Because, since it's 0 over 0, since we're getting this form 0 over 0 when we do our direct substitution, then that means that the value of a is making the denominator 0. So we want to find another function, h of x, that is equal to our f of x over g of x, but it's equal in every place except for at x equals a, over some interval containing a. To do this, we may need to try one or more of the following steps. If f of x and g of x are polynomials, then we should factor each function as we did in the previous example. We factored, and then we cancel out a common factor and cancel out any common factors. Part B, if the numerator or denominator contains a difference involving a square root. So if the numerator or denominator contains a difference involving a square root, we should try multiplying the numerator and denominator by the conjugate of the expression involving the square root. We'll see an example of that hopefully pretty soon. And then part C, if f of x over g of x is a complex fraction, so they're definitely tackling all the possible cases. If f of x over g of x is a complex fraction, then we should just simplify that complex fraction. And then part 3, we apply the limit laws. So let's see if, yeah, it looks like they are going to, I haven't read this ahead of time. So it says here, the next examples demonstrate the use of this problem solving strategy. So 2.17 illustrates the factor and cancel technique. 2.18 shows multiply by a conjugate, and 2.19 shows simplifying a complex fraction. Okay, this is a fantastic book here. They give us lots of nice examples. So let's take a look here at 2.17 really quick. So the limit as x approaches 3 of x squared minus 3x over 2x squared minus 5x minus 3. Now, if we tried to say, well, let's just plug in 3. This would be 3 squared minus 3 times 3 over 2 times 3 squared minus 5 times 3 minus 3. This is going to be on top, 9 minus 9, which is 0 on top. And then on the bottom, we get 18 minus 18. And you see that this is an indeterminate form, 0 over 0. Uh-oh. We can't, well, that's not the limit there because that's not a number. That's an indeterminate form. So the answer is not 0. The answer is not infinity. The answer is not 1, at least not yet. We don't know necessarily yet. So what we should do is let's try factoring both the numerator and denominator. The top is somewhat easy to factor. So this is equal to the limit as x approaches 3. We can just factor out an x from the top and we get x minus 3. Now, hopefully the bottom has a factor of either x or x minus 3 in it. And so I'll factor this up here because I might need a little bit more room. 2x squared minus 5x minus 3. And so I'll think of two numbers that multiply to 2 times negative 3 to negative 6, and two numbers that add to negative 5. Those two numbers are going to be, oh yes, they would be negative 6 and positive 1. These multiply to negative 6 and they add up to negative 5, yes. So my middle term, 2x squared, my minus 5x is going to become a minus 6x and a plus 1x. And this is going to allow me to factor by grouping. My first group of terms, my first two terms, I'm going to factor out the greatest common factor, and that's going to be 2x, and that will leave me with an x minus 3 inside of my parentheses. From the second set of two terms, I got to factor something out. So I'm going to factor out a positive 1, and then that's going to leave me with an x minus 3. Okay, and then I can factor out the x minus 3 times 2x plus 1. Okay, so my bottom is going to be x minus 3 times 2x plus 1. And so notice these x minus 3s will cancel, and I can cancel them now because I am here in a limit. The limit of this function, we can call this function here f of x, is equal to the limit of this new simplified function, x over 2x plus 1. The functions are not identical to each other everywhere. They're identical everywhere except for at x equals 3. But their limits are going to be equal. And so now we can do direct substitution. This is going to be 3 over 3 times, or 2 times 3 plus 1. And so this is 3 over 7. Boom. We've calculated the limit. Let's just read through the this thing here. Let's see if they did it exactly the same. The function f of x is undefined for x equals 3. In fact, if we substitute 3 into the function, we get 0 over 0, which is, it's not undefined. It's an indeterminate form. To be more precise here, is an indeterminate form. Factoring and canceling is a good strategy. So they factor it, they cancel out the x minus 3s. Therefore, the limits are equal. They plug in 3 and you get 3/7. All right, very good. All right, evaluating a limit by multiplying by a conjugate. Okay, so, okay, let's go ahead and take a look at how to do this one. They kind of talked about how to do this one in the problem solving strategy. Let's go ahead and do it. And again, for these examples, I do kind of like to write it out. So whenever you have a limit that has a square root minus or plus another term, we can multiply by the conjugate. We should officially check if direct substitution is going to work for us. So I'm going to do that up here. The limit as x approaches -1 of the square root of x plus 2 minus 1 over x plus 1. Let's go ahead and plug in the square root of -1 plus 2 minus 1, -1 plus 1 on the bottom. And then so we see this is the square root of 1 minus 1 over -1 plus 1 on the bottom. We can just immediately put 0. Notice this is 0 over 0. This is an indeterminate form. We need to, this is an indeterminate form. We can't say, you know, what value this has without simplifying first, right? Using some sort of other method. And so since we see that there is a radical on top, plus or minus some number, in this case, -1, what was the problem solving? We said, if we see a numerator or denominator containing a difference involving a square root, we should try to multiply the numerator and denominator by the conjugate. So that's what we're going to try to do here. The conjugate here is going to be the square root of x plus 2. It's going to be the same terms, basically, the square root of x plus 2 and a 1, except instead of a minus, we put a plus in the middle. And we need to multiply both the top and the bottom by this conjugate. Now, what does this do? This kind of does simplify things a little bit because we multiply these square roots, and this is going to be equal to the limit as x approaches -1 of the square root of x plus 2 times the square root of x plus 2 is going to be x plus 2. Since we multiply by conjugate, notice we're going to get +1 times the square root of x plus 2. And then we're going to get, we keep multiplying, -1 times the square root of x plus 2. Notice those are going to cancel. That's very nice. That's a nice property of multiplying by a conjugate. And then finally, -1 times a +1. This is going to give us a -1. Okay. In the denominator, yeah, we can multiply this out. Let's go ahead and multiply. Let's see what we get. X times the square root of x plus 2. X times 1. 1 times the square root of x plus 2. And 1 times 1. Okay. And here we're going to get some things that cancel. We said that this positive square root of x plus 2 and a negative square root of x plus 2 are going to cancel. And then we can just combine like terms in the top. And we have x plus 1 on top. And then on the bottom, what do we get? Nothing that can really cancel on the bottom, it doesn't look like. So let's go ahead and just write what we have. X times the square root of x plus 2 plus x plus the square root of x plus 2 plus 1. Now let's try direct substitution. Oh, excuse me. Dang. Yeah, I made a mistake there. Just looking at the solution, there's actually no mistake, but what I should do is, this is going to take us a longer way around if I try to do this. Yeah, unfortunately, I multiplied the bottom out, right? I shouldn't have multiplied that out, and we can actually see why. It's let me write this one more time in its factored form, and notice we would have x plus 1. Yeah, so good thing we haven't gone too far with this, times the square root of x plus 2 plus 1, right? Instead of multiplying this out, this is correct, actually, if we multiply this out, but I don't have to multiply that out. And the reason that we shouldn't multiply it out is because notice we have a common factor in the numerator and denominator. So we should actually leave that in its factored form so that we can cancel those. And now notice that those x plus 1s canceled, and the x plus 1s were where we were having our issue, because the x plus 1 in the denominator was getting us a 0 when we plugged in that x equal to -1. Right? We would end up with 0 over 0 if we tried plugging in -1 right now without canceling. So we make that cancellation, and now we have 1 over the square root of x plus 2 plus 1. And hopefully now we can do a direct substitution. All right, I'm being a little bit sloppy here with my notation by not putting my limit. So let me go ahead and put that in. I'll put it in red here just to limit as x approaches -1. These margins are kind of small here. The limit as x approaches -1. And so now, so technically I should have those limits each time I write a new equal sign. So now let's do direct substitution. 1 over the square root of -1 plus 2 plus 1 equals 1 over the square root of 1 plus 1 equals 1 over 2. Our limit is 1/2. Okay. All right. So step 1, we see that there's an indeterminate form right here. Yes. So we multiply by the conjugate in the numerator and denominator. we then multiply out the numerator. We don't multiply out the denominator because we are hoping that the x plus 1 in the denominator cancels out in the end. Okay, yeah, I mean, oh yeah, I mean, you can see that they're going to cancel right there. And then so then we cancel, and then we apply the limit laws. We do direct substitution there. All right. I mean, limit laws end up working out to direct substitution in most cases. All right. All right, very good. Let's see, how much do we have left? Oh my. Oh my. Okay, so maybe we'll split this up into two parts. It is late on Friday as I'm recording this. So we'll do one more, and then that will be maybe a good spot to stop. So evaluating a limit by simplifying a complex fraction. This is a complex fraction here where you have like a fraction inside of a fraction, right? So you have in the numerator, you have fractions. And so we'll simplify this. And how can we simplify? So in the solution, the first thing that they do is notice that this has the form 0 over 0, an indeterminate form at 1. So if you were to do direct substitution, you would get 0 over 0. Okay, so this needs to be simplified. You should try direct substitution in the beginning because it might just work and you'll be done. But if it doesn't work and you get an indeterminate form, then maybe you have to simplify your complex fraction. So let's go ahead and take a look. How would we simplify this? Well, 1 over x plus 1 minus 1 over 2 over x minus 1. One way to do this is to get a common denominator. And there's, there are a couple ways to do this. Now, I'll show something that's slightly different than what they have in the textbook. If I want to get a common denominator, I have to multiply this denominator here by 2, and I have to multiply the other denominator by x plus 1. Okay, so then this is going to give me, what is this going to give me? 2 over 2 times x plus 1. And let me write my fraction bar a little bit shorter. That's the first fraction. Then minus the second fraction on top is going to be minus x plus 1 over 2 times x plus 1. Notice we have a common denominator in the numerator now. And then, since we have a common denominator, we can combine those two fractions in the numerator. Now, keep in mind that this negative here needs to be applied to every term. If there are multiple terms there, that's a common thing that students always forget. So we would have 2 minus x minus 1 in the numerator. The denominator is 2 over x plus 1. And then there's still a denominator of x minus 1. Now, if you want to be, if you want to see the steps here, we can convert the denominator into a fraction itself by putting x minus 1 over 1. And the reason that we want to do this is to simplify this. I'm going to combine like terms here, just since there's 2 minus 1. I'll combine those two terms. And that is going to be 1 minus x over 2 times x plus 1. Now, how do we divide a fraction by a fraction? We multiply by the reciprocal of the second fraction. So I took this fraction here, I flipped it around, and I multiply by it. And it doesn't seem like anything cancels right off the bat here, but we can take a close look at this 1 minus x here. 1 minus x is the same as, I'm just going to flip the terms, negative x plus 1, right? Because this is a positive 1 minus x. And so if we factor out a negative 1 from this, we should notice that you could factor out a negative 1 and we get x minus 1. And so that means that 1 minus x can be written as negative 1 times x plus 1. There's also a times 1 in the numerator. I'm just multiplying these things together. And why did I put a plus sign there? It should be a minus, of course. I just wrote it up above here. 1 minus x, we said, can be replaced by -1 times x minus 1. And on the bottom, 2 times x plus 1 times x minus 1. And then you see that there are x minus 1 factors in common. And so we can cancel those. And so that means that our limit, the one that we originally started with, as x approaches 1, is equal to the limit as x approaches 1 of, if we canceled those two factors, it would be -1 on top, and on the bottom, we would have 2 times x plus 1. And now we can do, hopefully, direct substitution. The things that we canceled were the x minus 1s, and the x minus 1s were the things that were giving us issues as x approached or became 1. Because when x became 1, the x minus 1s both became 0. So that's where we're getting our 0 over 0 from. Now that we've canceled those out, there should not be a problem with direct substitution. This is equal to -1 over 2 times 1 plus 1. This is -1 over 4. Our answer is -1/4. Let's check the answer. Yes, that is the answer. Let's just read through it quickly and we will stop. So we simplified the algebraic fraction by multiplying by, so they multiplied by 2 times x plus 1 over 2 times x plus 1. They multiplied by what we call the least common denominator, the LCD. You may have heard of that before. That's an alternate way of doing it as well. Next, we multiplied through the numerators. Do not multiply the denominators because we want to be able to cancel the factor of x minus 1. Okay. Okay, sure. Yeah, you might know ahead of time that, because x is approaching 1, the x minus 1 is giving you a 0 in the denominator. But yeah, so we don't really want to get rid of this x minus 1 by multiplying that denominator. And hopefully the x minus 1 cancels somehow. So then we simplify the numerator. We had the x minus negative x plus 1 ourselves as well. And then what you do, you factor out a -1 from the numerator, and notice what you get now, a x minus 1 and an x minus 1 in the numerator and denominator. Then we cancel those common factors. The limits are equal, and so our answer is -1/4. All right, so nice. Evaluating a limit by simplifying a complex fraction. Now, example 2.20 does not fall neatly into any of the patterns established in the previous examples. However, with a little creativity, we can still use these same techniques. So example 2.20 is evaluating a limit when the limit laws do not apply. Okay, so we will stop here and I will leave you in suspense. And then we will pick this up and I will make a part 2 to this video because it is very late where I am or when I am. And I don't want to finish this whole thing right now. But we have some good stuff like the squeeze, squeeze, squeeze theorem coming up. So stay tuned for the next video.